Okay, what we're looking at here is a rational function, which is a function where I have a polynomial in my numerator and a polynomial in my denominator, commonly referred to as n of x on the top, your numerator, and d of x on the bottom is your denominator. There's a few components, and they're on the side here. They're also on your foldables. So we're going to look at how to find these components, and also I'm going to sketch a rough graph of this polynomial, or this rational function, excuse me. So the first thing I need to do is look for a hole, which is a gap in the graph. It's just one point, one ordered pair where the graph doesn't exist. And this happens because there's a factor on the top and a factor on the bottom that match. And so what happens is you would end up with 0 over 0 at that point, which is undefined. It doesn't exist. So what happens is there's an open circle on the graph at that ordered pair, but the rest of the graph continues as with the asymptotes, the intercepts, all that jazz. So first thing I want to do in order to look for a hole is factor the top and bottom. So I'm going to factor up here, and I realize I have x squared minus 4x plus 3. Factors of 3 that add to give me 4 are 3 and 1. Signs are the same. They're both negative, so x minus 3 times x minus 1. On the bottom, I'm looking for factors of 5 that subtract to give me 4. Signs are different, and the bigger sign is positive, so I have x plus 5, x minus 1. And what you notice is we have this common term of x minus 1. Keep in mind, that's a factor. That's not the 0. So if the factor is x minus 1, then my 0 must be x equals 1. So at x equals 1, I have a hole. What I'm going to do now is for the rest of my work, I'm going to use my reduced function. I'm going to use x minus 3 over x plus 5. This is now my function for the remainder of the problem because I got rid of this hole. Otherwise, I'm going to keep running to that do not exist. What I need to do is I need to evaluate the function at 1 to find the corresponding y value. So I'm going to take 1 and plug it into the function here, 1 minus 3 over 1 plus 5, and I end up with negative 2 over 6, negative 1/3. So the hole is actually at the point 1, negative 1/3. So to find the hole, I factored, I looked for the common term. If there is one, there's not always a hole. And then what I ended up with, and there could be infinite number of holes, however many common factors you have in top and bottom, I take the x value, I plug it into the reduced function and find the corresponding y value. So this is going to be an open circle at the point 1, negative 1/3 on my graph. Okay, the next component up is my x-intercept. So how I'm going to find my x-intercept is I'm going to take my numerator and set it equal to 0. The x-intercept, which is your x-axis, is where y equals 0. So I'm going to say, when will the function be equal to 0? Well, anytime I have a 0 in my numerator, anytime I divide 0 by something, the answer is going to be 0. So I set the top equal to 0. Remember, my top is just x minus 3 from now on. Set it equal to 0. I find I have an x-intercept at x equals 3. So I'm going to plot that on the x-axis in a minute. My y-intercept, I evaluate the function at f of 0, right? The y-axis is the line x equals 0, so I'm going to plug 0 into the function. So I evaluate the function at 0, meaning I take 0 and plug it in on the top. I take 0 and plug it in on the bottom, and I find I have a y-intercept at negative 3/5. So on my y-axis, I'm going to plot a point at negative 3/5. Next up is my vertical asymptote. This is where the graph is undefined. It's a vertical line up and down. Remember, we show asymptotes on the graph with dotted line. They're not actually part of the function, they shape the function. So what I'm looking for here is I take my denominator, which is just x plus 5, I set it equal to 0, and I solve. I want to know when will the denominator be 0, and I have a vertical asymptote at x equals negative 5. Horizontal asymptote is the tricky one. It's the one with a lot of steps. If you remember, I compare my numerator degree and I compare my denominator degree. So lowercase n is the degree of the numerator, which in this case is 1. Lowercase m is the degree of the denominator, which in this case is also 1. So what I do, the rule here, when n equals m, is a y equals line at the leading coefficient. So my leading coefficient on the top is really a 1, and my leading coefficient on the bottom is also really a 1. So 1 over 1, I'm going to have a horizontal asymptote at the line y equals 1. I have a spot here for slant, but keep in mind slant is only if the degree of the top is exactly 1 more than the degree of the bottom. In this case, that's not true, so I don't have a slant asymptote. So here I would put none. I can only have horizontal or slant. I can't have both. So my last piece here is that I'm going to find additional points. Before I do that, I'm going to add a graph and sketch the pieces that I do know, because that's going to give me an idea of what additional points should I even be looking for. So first thing I do, get my XY axis all lined up, and then I'm going to plot the pieces of information I just found. Additional points are just going to give me a better shape, a better idea of what my graph is going to look like. Keep in mind this won't be exact, it's a sketch, but we're going to use the pieces we have to come up with a pretty good idea. So I have a horizontal asymptote at the line y equals 1, so at y equals 1 I draw a dashed line, that's how I show my asymptote. I have a vertical asymptote at x equals -5, so 1, 2, 3, 4, 5. I have a y-intercept at -3/5, so between 0 and 1, or 0 and -1, I'm sorry, I have a point there, so somewhere right there. I have an x-intercept at 3, so at 3 I have an x-intercept, a point on my x-axis, and then I have a hole at the point 1, -1/3, so 1, -1/3, somewhere in here. I put an open circle. I realize that's not at 1/3, the other one's at 3/5. It's a little exaggerated, but I want to show, even if it's exaggerated, that there is in fact a hole there. I want to show there's an open circle. So what I'm going to do in terms of additional points is I want to know what's going on. Let me get different colors so we can see. I want to know what's going on over here on this half of the graph, on the other side of the asymptote. And I also want to know what's going on over here. I have no idea. I have those 3 points, but I have no idea what's going on there. So I'm going to do my additional points. I'm going to use, let's say this is -5, so I'm going to use -6. And I'm also going to use, at this 0, I'm going to use -1. So 2 easy numbers. I plug them both into my original function. So -6 minus 3 over -6 plus 5 is going to give me -9 over -1, which is 9. And -1 is going to give me -1 minus 3 over -1 plus 5. I end up with -4 over +4, which is -1. So now I plot these points. I have a point at -1, -1, and I have a point at -6, 9. 1, 2, 3, 4, 5. Gonna be right off my graph. I'm gonna do -8 as well, just so I have a better idea of what's happening on the graph. So when I plug in -8, sorry, this is going to get a little messy, -8 minus 3 over -8 plus 5, I get -11 over 3, which is 3 goes into 11 3 times with 2 left over. So this is just going to give me a picture of what's on my graph in the window that I'm looking at. So at -8, 5, 6, 7, 8, oops, sorry, I realized I forgot a negative sign here. So it's actually going to be a -3. -8 plus 5 is -3. This should be a positive. What got me there is I shouldn't be going underneath the asymptote. Remember, I can't cross it. So this is actually should be above. So at -8, I have the point 3 2/3, 5, 6, 7, 8, 1, 2, 3, and a little more, 2/3. That's just going to give me an idea of what the part of the graph looks like. So now I'm going to take, remember, just like a polynomial function, smooth, rounded, curves. I do my best approximation, right? I don't know much about the rest of the graph. I could find additional points, but I can use my asymptotes, which approach but don't touch, to get a better sketch of my graph. And there's a rough sketch of your polynomial function, I'm sorry, with your rational function, all the pieces that go with it.